Hey, welcome back. Today we're going to talk about a couple more things you can do with vector functions. Um, so the first thing we're going to talk about is arc length. And to set the stage, let's first talk about the way we've approached calculating area and volume in single variable calculus. So when we were dealing with single variable calculus, we calculated the area of under a curve by calculating a whole bunch of little bits of area, right? We said, oh, the area under the curve, let's add up a whole bunch of rectangles, and each of these rectangles was calculated by some little bit of x distance times the height, f of x. So in some sense, what we were really doing is saying, well, area is a sum of a whole bunch of little bits of area. Then we did the same thing to calculate the volume of a revolution, a solid of revolution, where we said, okay, if we're going to take a function and we're going to revolve it around the x-axis, then in order to figure out what the volume is, well, a volume looked like a very thin cylinder, and the area of a cylinder is pi r squared times the height, dx. So we had a little bit of dx. The radius of this cylinder was f of x. And so that gave us this formula for the volume. The volume of the whole thing was what happens if you broke down the volume into a whole bunch of little bits. Okay, so now we're going to talk about the length of a curve. So we're either talking about a curve in 2 dimensions, right, defined by a parametric equation, or we're talking about a curve in 3 dimensions, and again, by some parametric equations. Okay, and so if we want to calculate the length of this curve, then we're going to break it up into a whole bunch of little bits of length. So the length of the whole thing is equal to a whole bunch of little d lengths from the start to the end. And so what we need to do is we need to come up with an equation for what the length of a little tiny bit is in terms of our functions. And so you'll see that this plan, the formula that we come up with, is going to look the same whether we're in 2 dimensions or whether we're in 3 dimensions. We're basically going to say, okay, well, if we're just looking at this little bit of length, dl, well, there's some change in x and there's some change in y. Or if we're in 3 dimensions, then we have this dl, we've got some change in x, we've got some change in y, and we have some change in z. Right, and we've already talked about the length in the length of these sides of a triangle, or the length of a path where we have some x, y, and z components. Right, what we're saying here is that dl is equal to the square root of dx squared plus dy squared. Or dl is equal to the square root of dx squared plus dy squared plus dz squared. Right, so if we're writing these things down in terms of what a little bit of length is, then you can write it down in terms of how little bit in x direction, a little bit in the y direction, a little bit in the z direction, if there's a z component. And you could imagine what would happen in higher dimensions. You'd have a w direction and a v direction and a u direction. You could just do that for every single direction that there is. So as we write down this formula, the integral of dl is the integral of dx squared plus dy squared plus dz squared. We realize that the dx, the dy, and the dz, our function isn't defined in terms of x, y, and z. It's instead defined as a function of time. So in order to say, well, how far does the function r of t go in the x direction for a small value of t, dt, well, we were looking at this curve, we're going along the curve, and for some amount dt, how far are we going along the curve? Well, the rate at which we're moving in the x direction, or in the y direction, or in the z direction, is going to tell us how far, if we have a little bit of dt, then the distance that we've traveled in the x direction is going to be the rate at which we're traveling times that little bit of distance, right? So this dx that we wrote up here as how far we're traveling in the x direction is actually best represented as a product of, this is the small amount of time, and this dx is the rate of traveling in the x direction. So what we're seeing here is this integral is actually best represented by dx dt squared plus dy dt squared. These are derivatives. And then we'll put the z part here as well. And then if you look at this, there's a dt in each of these pieces, which they're all squared, and then we can all factor them out. And so putting this all together, if we take this dt and we factor it out, then what we get is that the arc length formula is going to be the derivative, the rate of change in the x direction as a function of t squared, plus the rate of change in the y direction as a function of t squared, and plus the derivative of z is as in a the rate of change of z as a function of t squared. All of that, the square root of that, times dt. And this is what you'd have to calculate if you want to go in and calculate it. We can write that in a much simpler form if we think of this as, oh, this is really the magnitude of a vector, which is the derivative of r of t. Remember, if r of t is equal to x of t, y of t, z of t, then when we take the derivative, we get x prime of t, which is dx dt. The y derivative of y of t, derivative of z of t. And so that's why plugging it in here, that's why we can write it this way. So let's do a quick example. Let's say we want to find the length of the curve. Here's a really nice curve. What's the length of the curve between t goes when t goes from 0 to 2 pi of this curve? All right, so this curve, let me switch over to just to see what it looks like. Oops, come back here. Let's switch over to see what that looks like. This is an example of a cycloid curve. Now, this is from section, if you want to read more about this curve, this is in section 9.2 of the book. This is a curve, basically, if you roll a wheel along a path, if you can figure out how the wheel travels, like one point on the wheel travels over time, and it follows this curve. So if we want to figure out what we're looking for here is this is what the curve looks like for many values of t. If we want instead to look for just from 0 to 2 pi, we get this curve that looks like this. And what we're asking when we're talking about arc length questions, what we're asking for is what's the actual length of this curve if you were to travel along it and measure the distance that you've traveled. Now you can see the answer is going to be at least 6, right? This is from 0 to 2 pi, so the length is 6, is at least 6, but it's bigger than 6, and we kind of also, it's almost like you could approximate it even better with maybe some triangles here. You can see it's going to be bigger than 7, but we should figure out exactly what it is. We can get Mathematica to do it, and maybe we'll do that in a second. But let's go back to our tablet, and let's do the calculations. So what our formula says is that we need to find r primed of t. I'm going to make this a bit bigger. So we need to find r primed of t. Okay, so we take the derivative of each of the components. What do we get? So the derivative of t minus sine of t is 1 minus cosine of t, and the derivative of 1 minus cosine of t is 0 plus sine of t. So this is r prime of t. And so what we need to do now is take the length of this curve, right? So now we need to take the length of r primed. So that's the square root of the first thing squared plus the second thing squared. Okay, so now we'll expand. What do we get? The square root of 1 minus 2 cosine of t plus cosine squared of t plus sine squared of t. And now if you look at this, you're starting to say, oh, this I think we can simplify, because cosine squared of t plus sine squared of t is equal to 1. So what do we get? We get square root of 2 minus 2 cosine of t. All right. So now we need to, so this is the length of r prime of t, and so what we need to now do is take the integral from t goes from 0 to 2 pi of square root of 2 minus 2 cosine of t dt. Okay, so to solve this, let's make a little bit of space up here, and we'll use a trigonometric identity. So our trig identity that we can use says that sine squared of x is equal to 1/2 of 1 minus cosine of 2x. So if we look at the structure of this, then what we need to do is we need to replace t by 2x. So, or 2x by t. So that's telling us that what we actually need is we need sine squared of t over 2 is equal to, maybe we'll put the 2 on the other side, 2 sine squared of t over 2 is equal to 1 minus cosine of t. So let's now substitute that in here. All right, this integral, I'll move it up here. I'll have to figure out a better way to organize this if I were going to do this again. So what do we get? We get the integral from 0 to 2 pi of the square root of 2. There's a 2 here that we're pulling out. Right, this is the integral from 0 to 2 pi, square root of 2 times 1 minus cosine of t dt. So the integral from 0 to 2 pi of 2 times 2 sine squared of t over 2 dt. And so we have the square root of 2 times sine squared. So this is equal to the integral from 0 to 2 pi of 2 sine of t over 2 dt. And then we let u equals, oops, if we let u equal t over 2, then du is equal to dt over 2. And so we get that this is the integral, and then we also have to change the bounds of our integration. So the integral from, so if u is equal to t over 2, then t, oops, right, we're taking an integral from u. So we get the integral from u is equal to 0 to u is equal to pi of 4 sine of u du. Okay, what do we get here? So we get 4, the integral of sine of u is negative cosine of u. U goes from 0 to pi. And so we get negative 4 times negative 1 minus 1, which is equal to 8. And so the length of this curve, oops, the length of this curve is then equal to 8. Which, that's sort of what we were saying. We were saying the length should be bigger than 7. And here we are, it's exactly 8. Let's get Mathematica to solve this for us, and then let's take a break. All right, so we want to integrate. What was our function? It was the square root of the derivative of t minus sine of t as a function of t squared plus the derivative of 1 minus cosine of t as a function of t squared. And we're taking the square root of that, and we want to integrate that where t goes from 0 to 2 pi. And what's it going to tell us? It's going to tell us that the answer is 8. So it's done all those calculations. We had to take a derivative of this function as a function of t. We had to tell Mathematica what the important variable is. Same thing here. We're taking the derivative of 1 minus cosine of t as a function of t squared, where t goes from 0 to 2 pi. All right, so let's take a break there, and we'll come back and talk about reparameterizing a curve based on the arc length. All right, see you soon.